All right. So the lecture today is about the differentiation theorem of Lebesgue. It's a beautiful piece of analysis, and the purpose of the lecture is to do the proof. And I will mention some other ingredients that I'll take for granted in the online meeting. So again, let's look at it together. So you have f, which is L1 log. So remember, L1 log means that the integral of absolute value of f on any compact set is finite. Theorem holds in RD. And it says that when you average f on a ball centered at x, okay, so you normalize, so that's really the average here, and you take the limit of that ball goes to infinity, then this actually averaging equals f of x almost everywhere, and this almost everywhere here is with respect to the Lebesgue measure. Okay, so this says essentially that L1 log of functions that are locally or fairly regular on most points. Okay, good. Now, what do you need to prove that? So we need a couple of ingredients that are important. So first of all, we need this average function, a for average. Depends on r and x, and it turns out that this mapping, as a mapping of Rx, is jointly continuous, so there's no measurability problem, for example, when we look at this set. So I'll mention that in the online meeting. Now the theorem 7, this is that tells you that the set of continuous function with compact support in RD is actually dense in L1. This was a result that can be proved from chapter 2. We'll just take it for granted. Again, I will do the more details when we meet online. Okay, good. So with this ingredient mostly, and also the measurability, the fact it's only continuous, we can do the proof. Okay, so let's start. So since f is an L1 log, I can just restrict to a compact set. This is a local property, right? It's about averaging on a ball locally, so no problem. I can just work on a compact set. Okay, so I want to show that the limit when r tends to 0 of the averaging minus f of x equals to 0 for some set E, okay, was of full measures. The complement is as measure 0. So we're going to build that set E. So for this, consider Gn, where this limit, so the lim sup, okay, to be on the safe side, I'm not sure the limit exists at this point, so the lim sup is bigger than 1 over n. So for each Gn, we'll actually show that the measure Gn is 0, and I have a countable union of set of measures 0, so by sigma additivity, this set has also 0 measure. Okay, so every Gn has measure 0, that's our goal. Alright, now here's the trick. Now, where do we use the fact that continuous functions are dense in L1, continuous function with compact support? So again, we can restrict to f in L1. So suppose we have a function which is continuous, then the statement is clear. Why? Because if it's continuous, the function g is continuous in RD, then on a compact set it's uniformly continuous, right? So I can take that ball small enough so that y is very close to x. And you remember uniform continuity, if y minus x, y and x are at a certain distance, small enough, then gy minus gx is smaller than epsilon, uniformly for all these y's. So if I have that, then I'm done, because the averaging of g is simply this, right, by definition. And so just replace gy by gx, you just do an error epsilon, and then you're done. Okay, so the statement is obvious for a continuous function. So if you want, the whole subtlety is about lifting this result for a continuous function to L1, and that's where we use the density. Okay, so this is the comment I will do later on Friday. So let's move on. So, all right. So again, the idea is to approximate f in L1 by some function g compact support. So since it's dense, let's take a g epsilon, which is epsilon away from f in L1. Okay, this is the L1 norm. So now I do what we call the 3 epsilon argument. That is, I have ARF minus F, and I just introduce G epsilon and its average, and use the triangle inequality. Okay? So I have 3 terms now. So one of them I know I can be made small by the limb sup because it's continuous. So that's good. This goes to 0, so I have 2 terms left, right? And remember that Gn is the set where this is actually bigger than 1 over n. So if this is bigger than 1 over n, that means either this is bigger than 1 over 2n or this is bigger than 1 over 2n. So I can separate the argument into 2. Okay? And now here's the interesting part. That's why it's a nice piece of analysis. We see 2 important inequalities. Okay, the first one we already saw. So I want to bound the measure of this set. So the measure of this set can be bounded using Markov's inequality, or Chebyshev if you prefer. So the measure of this set is always smaller or equal than the inverse of that. So that's just 2n. In this case, the integral of the absolute value of my function here. Okay. So this is the L1 norm, which we know is small, right? It's actually smaller than epsilon. So this is small by taking epsilon tends to 0. N is fixed, remember? We just proved we showed it measures 0 for every n. So that's it. Great. The other part is a bit more tricky. Okay, so the other part, I also have this set, but now I have the averaging. All right? And I have this limit. Limb sup. Now, so now how can I do this? So here I can take the absolute value inside. So there's a G epsilon here, here, and here. Okay, so I can just take the absolute value inside. That's the AR, and that's what it is. All right. So now I get an equality which looks a bit like the Markov inequality. Okay, so it's a measure of a function which is positive, bigger than something. So this should be smaller or equal than the inverse of that. Okay. Now I have a constant C. I will explain it later, and the norm of this. Okay. But here, it's as if I forgot about the limb sup and AR, right? It's as if I just applied a Markov blindly. So this is an improvement on Markov's inequality. Markov's inequality would give you the same thing with the norm L1 here of that limb sup included in there. You don't have it, and that AR too. You don't have it here. So it's an improvement on Markov inequality. And this is the maximal theorem here. Now, if you're a probabilist, this is very close to something called the due maximal inequality for a martingale. Okay? So when you have some extra structure, and here the extra structures come from the average, and sometimes you can do better than the Markov's inequality. All right? So let's just assume this is true now. Then you do the same thing. Epsilon tends to 0. I have that. And I've shown that MGN is 0 for every. Okay, so this is a very nice proof using nice inequalities and this density of continuous function in L1. And again, remember that the whole point here is that the argument is obvious for continuous function. All right. Now let's say a word about this maximal theorem. So it says the following again. So the maximum of the soup, so instead of lim soup I have soup, okay, but it's the same kind of statement. 1 over m, the averaging of the absolute value of f bigger than a, is smaller or equal than this 3d, which is the constant. See that here. D is the dimension, so it's really a constant, divided by a, okay, that's the inverse from Markov, and simply the L1 norm of f. So you again forget about the averaging and R and the soup. Okay, we call it maximal because of the soup. Okay, it's maximum of this, and the express structure comes from the averaging. All right, so let's do this proof, and that will end the lecture. All right. So again, remember that one fact is that ARF is jointly continuous. And so therefore, when I look at the set of X, when the soup of the averaging is bigger than A, I can always write that as the union over R, because this is the soup, okay, of ARF bigger than A. Now, why is that Lebesgue measurable set? Now, it might be a bit unsettling because here I have an uncountable union, but you have a continuous mapping here, right? And you're looking at the preimage of an open set of a continuous mapping. Therefore, this is open. And a union of open set could be uncountable is also open, all right? So this set is actually open. So there's no problem in considering an uncountable union here, all right? And we call this set EA. Now I want to show that this set EA has measure bounded by this factor. All right. So again, these proofs are not easy, okay? There's several ingredients, but this nice piece of analysis. So that's why we have to kind of study them. All right. So, okay, so write EA for this set. Okay. So if again, X is an EA, that means it's here for some R, and I'm going to call this R Rx for fixed X, right? So for each X, I have some ball, BRX, okay, that comes from in the averaging here, such that the integral over the ball is bigger than A and B. That's just explaining what the A is, all right? Okay, now what you want to do is actually, so what I have is these EAs, okay? That's in my picture, this is the orange, that's the set E, all right? And for every point here, I have a ball. So I have an uncountable number of balls, possibly, and the covering E, obviously. And I want to extract, obviously, a finite number and use additivity of my measure. That's the idea here. So how can I extract a finite number of balls, at least countable number of balls, so that I can add my measure? So I'm going to use a compact set. So how can I get my compact set? Well, I know my Lebesgue measure is regular, right? So we can take a compact set which is included in EA, whose measure is really close to EA. I can do that by regularity, okay? And now obviously all the balls cover K. So I know I have a finite set of ball B1 up to Bn prime that cover K, all right? Those are the balls that are in pink. Okay, now here comes another set of balls, the balls A's, okay? This is not the same as averaging, it's a bad notation. The A's are some sub-collection of balls of the B's, okay? So what you do, you have a finite number of balls. So I can take the biggest, that's A1, okay? Then I take the second biggest, which is this joint of A1, that's A2, all right? So I guess my picture is not really good because so this ball is actually bigger. Okay, so let me just say it. That's probably better. So A1, so B covers the K. So I take A1 the largest, then A2 the largest of the B's covering K. which are disjoints from A1, and so on. Okay, so you get a collection of balls, A1 to AN, it's a subcollection of the Bs. And if you had a B in the original covering, which is not selected by this process, that means that at some point you intersected AJs. Okay, one of the AJs. Okay, no disjoint. We're not disjoint. And let's say that B intersect, the largest ball it intersects is AJ. All right. So by this procedure, then B must be disjoint of A1, A2 on AJ minus 1. Okay, just by construction. And what happens here, and that's the picture here, and that's where the 3 come from, then, okay, so intersect AJ. So if it intersects the worst case, right, so this is B and this is AJ. Okay, and so this is the worst case. And now the claim is that B contains 3 times AJ. Okay, so a ball of 3 times the radius. Okay, so this is kind of clear here. So the radius of B has to be at most the one of AJ. Okay, otherwise you would have selected B instead of AJ. So if you think about it, B has radius at most AJ. So what happens is AJ has a certain radius which is bigger or equal to B. So if that's the worst case of intersecting, right? So I just barely touch. So I take 3 times this radius. Then this ball with 3 times the radius would include B. All right. So that's the conclusion. I'm going to put it in. This means that B is contained in 3 AJ. All right, then we're done. Okay, after all this work, that MK is smaller or equal than the covering with the balls, which is smaller or equal than the ball that contains it, 3 AJ. I can take the 3 out. Then I get 3D. Remember when in RD, so 3 times the radius, I get a factor R to the D. And those AJs are disjoint, so I get the sum of MAJ. Okay? So now we're done. We'll just go back to this equation. And I just write it in terms, so this is where all the balls, so I selected sum of the ball, I call them AJs. You get 3D sum of MAJs is smaller or equal than 3dA, the sum over the integral over the union of the balls. And obviously this is small equal to integrating on everything, which is the FL1 norm. So in conclusion, we get that measure of K is smaller or equal than a constant divided by a L1 norm of F. All right, and remember that K was a compact set that is included in the set we were looking at. And by regularity, I can take that K very close to E in measure, and therefore this inequality is also satisfies that MEA. Okay, not an easy proof. The first time you see that, I remember I was quite confused. But again, uses quite nice pieces of analysis, so it's worth actually looking at several times. All right, so that proves. So let's go back to the Lebesgue differentiation theorem that averaging of a ball of F is equal to F of the center of the ball, M almost everywhere. And again, we said the consequence of that already. If I look at R, that gave us a new look at the definition of being absolutely continuous with respect to the Lebesgue measure. So in particular, it shows that the Radon-Nikodym derivative in that case is just equal to the classical derivative at least almost everywhere. Okay, which is essentially the fundamental theorem of calculus. All right, thank you.